This week is week 2, and it's about hypothesis testing. We'll also talk a little bit about effect sizes, which, as we'll see, those are two slightly different things. As you'll see, when we compute a test statistic, we want to know whether or not the test statistic is reliable and whether or not it's meaningful. And hypothesis testing is a way of going about testing whether or not the test statistic is reliable. As if the effect that we observe is statistically significant, if it's reliable, if it's outside a 95% confidence interval, etc. These all mean more or less the same thing. A test that is statistically significant is said to be reliable. And if it's reliable and it's statistically significant, that's evidence for the alternative rather than the null hypothesis. The null hypothesis is that the two groups you are sampling from are from the same population, okay, and that they have similar means, and that the difference between the means is 0. So when we say the null hypothesis, the hypothesis is that there is no effect, that we gave somebody a treatment and we didn't create a new population. The means from the people who got the treatment and the people who didn't get the treatment are the difference between those means is 0. It's the same population. We haven't created a new group. However, this is an important point. When a test statistic is not significant, when a test statistic is insignificant or not significant, we haven't proved the null hypothesis. We haven't proved that the scores did in fact come from the same population, at least with the statistics that we're going to cover. So we can reject the null, but we can't prove the null. We can reject the null hypothesis, but we can't prove the null hypothesis, at least with the statistics that we're going to be talking about. All the statistics that we're going to cover in this course are based on a rejection of the null hypothesis. The hypothesis that there is no effect. The means are the same. Statistical significance is an indicator of whether or not the difference in means is greater than 0. I'm going to say that one more time. Statistical significance is an indicator of whether or not the difference in means, the difference between two means, is greater than 0. Statistical significance does not tell us how great the difference between the means are, or how large the difference between the means are. The p-value, which is often used as an indicator of statistical significance, is also the type 1 error rate. So if we think back to what the type 1 error rate is, the type 1 error rate is the rate at which we're willing to accept false positives. Okay, so it's kind of if we ran the test 100 times, how many false positives are we likely to get? That's what the p-value is. That's also what the type 1 error rate is. So if the p is less, if you run a statistical test and you get a p-value of less than 0.05, which is a commonly used threshold for statistical significance, there's nothing special about p less than 0.05. It's just the one that kind of caught on. If you run a statistical test and your p-value is less than 5.05, then that means that if you ran 100 tests, 5 of those tests would be false positives, just from chance alone. The p-value indicates how likely it is that the difference in the means being greater than 0 is just due to chance. So we could have two groups and we could take their means, and they could have a very large difference in the means. That might just be due to chance. That's what the p-value indicates. How frequently, just due to chance, are we willing to reject the null hypothesis, and it be a false positive. So how is the test statistic computed? Well, basically, the difference between the group means is scaled by the amount of variability in the two groups. I can't think of a statistical test that doesn't boil down to this in one way or another. And it's we show it here. This is the gist. We take the difference in the means, that we would consider that to be the effect, and we divide it by the error, the kind of how spread out the scores are from their own mean. And that's the test statistic. In the case of an independent samples t-test, the difference is in the group means is scaled by the sum of the variability of the two groups. So in the independent samples, we would have two sources of error in our denominator, one for each group, and they're not directly added up, but they are added up in one way or another, as we'll see in the formula. They're pooled. It's called a pooling of variability. We pool the variability of the two groups, and then we see how big the effect is given the error from these two groups all added up. This independent samples t-test is used for between subjects designs. In other words, we wouldn't expect similar variability in scores between different groups of people. They're different people. So we pool the two sources of variability. This has the effect that a bigger difference between the means is required for statistical significance, because the difference is scaled by a larger amount of variability in the case of the independent samples t-test. So this test is a little, between subjects designs tend to be a little harder to find statistical significance usually. You need a bigger effect because the variability is added up. Compared to the case of the paired samples t-test, where you only have you have the variability for the whole group. It's not added up. The paired samples t-test is used to test the difference in means within a subject. In this case, we only sampled one group, and thus the variability that the difference in means is scaled by is smaller. And a smaller difference in means can result in a significant effect compared to the independent samples t-test. So it's a little easier to find effects in a paired samples t-test because the error term is going to be smaller. In this regard, put another way, paired samples t-tests and most other statistics for repeated measures tend to have more statistical power than between subject statistics. Statistical power is the opposite of the type 2 error rate. When we have a high type 2 error rate, if you remember, that means our test is a little too conservative when we have a high type 2 error rate. There may be real effects that we fail to detect. We're being a little too conservative. So statistical power is the opposite of that. When we have high statistical power, we have a low type 2 error rate. We're not going to miss those subtle effects. And that's the case with the paired samples t-test. It has good statistical power, and as is the case for other repeated measures designs. Like every statistic, there are some assumptions. For the t-test, the difference between the means should be normal. The distribution of scores might not be normal, but the difference between the means should be. And you just want to check that out before you run your statistics. You can take each score and subtract it from its corresponding score. So you would take subject 1's before treatment data and subtract it from their after treatment data, or from another subject's after treatment data if you're doing between subjects designs. And then you would have a bunch of differences. You used to have 2 sets of scores, now you have 1 set of scores, the difference between the 2 conditions. And those differences should be about should approximate a normal distribution. For the t-test, you also want to be sure your data were measured at least at the interval level. And then for the independent samples t-test, it's also important that the variance is homogeneous across the distribution of scores. If it's not, there are statistical adjustments for the t-test for when the variance is heterogeneous, when it's not homogeneous. Heterogeneous is the opposite of homogeneous. The independent samples t-test also assumes that the scores are independent of one another, and that's the last one's a bit of a no-brainer. The paired samples t-test is for, it's also called the dependent samples t-test, is for dependent scores. The independent samples t-test is for independent scores. So here are the formulas. Take a second to look at these formulas for the paired samples, this one up top, and the independent samples t-test. Like I said previously, the t-test takes the difference between the means. Here's the D is for difference. And compares it to the difference expected under the null hypothesis. Now, if you remember, the null hypothesis is that there is no difference in the means. So in most cases, it's the difference minus 0. And then you divide that difference by an estimate of the variability of the scores in that sample. How much you take each score and you subtract the mean from it, and how big is that difference? That's what we're talking about when we're talking about variability or deviation. In this case, the difference in means is scaled by the standard error. This is the formula for the standard error on the bottom. It's the standard deviation divided by the number of samples, the number of subjects or observations. The standard error is an estimate of how far the sample mean in most cases could be from the population mean. So if we were trying to guess the mean of a population and we measured a bunch of different people, let's say from different states or different schools or whatever, how far would we expect any given sample mean to be from the population mean? How far would it have to be away from the population mean before we started thinking, well, maybe this sample mean is from a special population? You know, maybe when we got scores from the people in Mississippi or Florida, you know, the people in the South are different than the people in the North. This is a different population. I don't know. Note that in the independent samples t-test, the denominator is comprised of 2 sources of variability. So this is essentially the same formula here, but now you're doing it for each of the different groups of subjects that you recruited. So here the difference is for within a subject, the difference between time 1 and time 2 for subject John, whatever, and then here it's the difference between all the scores for group 1, John, Mary, and Sally, and group 2, you know, Jim, Dick, and Jane. And so this explains why it's a little harder to find an effect in between subjects designs. This has greater power because this denominator tends to be smaller.